Alrighty, section 4 then. We're getting to work with the sampling, distributions, and estimators. The main objective of this section is to understand the concept of a sampling distribution of a statistic. We also will see that some statistics are better than others for estimating population parameters. This is going to be a section that is a lot of conceptual information. I will tell you now, so you're not stressed out throughout the rest of the lesson, there's only 3 questions on the homework. So it is not an assignment and not a section that we're really working with practicing a lot of the stuff. This is a lot of the conceptual. We will build on this in section 5. So understanding what's going on in this section is going to help us to be able to do the next stuff. So, definition. The sampling distribution of the mean is the distribution of sample means with all samples having the same size n taken from the same population. Okay. All right, so what this is telling me, a couple different things to pay attention to. One is that we're keeping it the same size. So I think I've got the next page having an example. If we look at an example of this, I want to select 2 of the values between the numbers 1, 2, and 3, with replacement being an option. So if we're looking for the sampling distribution of the mean is the distribution of sample means with all samples having the same size n taken from the same population, then when we're looking for getting this sampling distribution here, if I'm trying to select 2 of the values 1, 2, and 3 with replacement, what's some options on what I could have? What numbers could I pick? 1, okay, 1 and 2, 1 and 3, 1 and 1, okay? I heard somebody say 2 and what? 3. We're doing it with replacements, so the order doesn't matter. So we've already got 2 and 1 in there. So we've got 2 and 2, or we've got 3 and 3. Now, if I did that, so these are my different sampling distributions I could have, what is the means of each of these? So if we use 1 and 2, what is the mean of those? What? 1.5? Of this one? Now, notice that these are doing the X bars because these are samples. So this is the sample mean of each of these. So this is the sampling distribution of the means. Out of all the different combinations I've got, these are the different possible means that I could get. So this right here would be considered my sampling distribution of the mean. Well, if I look at how that distribution looks, so when we're looking at doing this distribution, we have 1, 2, and 3 are things we could have. When we're looking at these, we had the first number was 1.5, second was 2, we had a 1, then we had a 2.5, then we had a 2, then we had a 3. Now, this is a very small sample space with a very small population to start with, but what kind of shape does that look like? Looks pretty close to a normal distribution. Okay, that's a little too high, but so it looks a lot like a normal distribution. If I had a sample size that, or a population that was much more than just 3 different members in the population, and I was doing samples that and having more than just a few samples to be able to look from, it's going to get to be closer and closer to being that normal distribution. So trying to look at what happens when we look at the distribution of the means, but keep in mind the key thing we have to pay attention to, it's the sampling distribution of the mean is the distribution of sample means with all samples having the same size n taken from the same population. So in this case we had the same size n, each sample was size 2, from the same population, and my population were just the numbers 1, 2, and 3. If I was trying to do it with statistics students and I was taking samples of size 4, then every combination of 4 statistics students would be in my new sample. And if I was looking, I guess, maybe at the ages of each of you guys, and I was looking at all those different combinations. Well, what we can say about these then, there's some properties that come from these sampling distributions. The sample means target the value of the population mean. That is, the mean of the sample means is the population mean. You're going to hear that one a lot, so kind of trying to figure out what in the world I just said. The sample means target the value of the population mean. That is, the mean of the sample means is the population mean. The mean of my sample means, so if I find the mean of all these sample means, if I add up 1.5 plus 2 plus 1 plus 2.5 plus 2 plus 3, so we'll have 5, 7, I make 10, 11, 12, 15. So if you add all those up, so if I add the sum of my sample means, we get 15. Divide it by how many there are, because I'm trying to find the mean of my sample means. And so we had 1, 2, 3, 4, 5, 6 values. What is 15 divided by 6? Yeah, why am I not coming out right? How about I add better? Because it's adding up to being 12. I added wrong. So this would be 5, 6, 7, 8, 9, 10, 11, 12. It adds to be 12. I was knowing I had issues because it wasn't coming out the way it should be. I knew it better be 2. So this is the mean of my sample means. Where I was finding every single sample that had 2 items in it, so all of the different combinations, found the mean of my sample means. Now, I knew that my answer had to be wrong because what is the population mean? What's the mean of 1, 2, and 3? 2. So the mean is going to be 2. The mean of my sample means was also 2. And I'm trying to remember how I want to write that. Written down. 6 divided by 3 numbers. So we're looking at the mean of my sample means being 2, and the mean of my population was also 2. Okay. I can't say never. Also, the distribution of the sample means tends to be a normal distribution. Now, these are, so again, this one came out to being tends to be towards a normal distribution. It's not going to be perfect when you're working with each of these different things, especially when you've got such a small population and such a small amount of samples that we're working with. It didn't give us that great normal distribution. If you had 100 the first 100 numbers, and you were picking 10 out of 100 numbers, and you looked at all of the different combinations, and you found the mean of all the sample means, it would be the exact same as the mean of all of the 100 numbers divided by 100, the sum of the 100 numbers divided by 100. It would still come out to being that same thing. And that was the case. You'd have a lot more numbers, and it would get to being showing that it's a nice normal distribution. So these properties, when we're talking about the distribution of the sample means, these properties are going to hold. If we look at the sampling distribution of the variance, this is the distribution of sample variances with all samples having the same size n taken from the same population. So when we go through and find the variance, trying to see I thought I had it in here. If we were taking the variance of each one of these. So refreshing memories on finding variance. slowly coming on. From our chapter 3, when we were doing the descriptive statistics, which one of these formulas in here helps me find my variance? Okay, use the standard deviation and do what to find it? Square it. So you're just looking at what's underneath that radical. Now this will be our shortcut that we would want to use, where it is the sum of the x squareds times n minus the sum of the x's squared, and dividing that by n times the quantity n minus 1 would be the way we're looking at it. It's really finding the difference between the value and the means, taking each of those and squaring them and dividing that by, or adding those together and dividing by n minus 1. If we did that back on this, oops, go back to the thing. I think actually I'm going to look at doing that one on these. Make myself some room. So if I'm finding the variance between these, then I want to look for the difference between my values and the mean. And so if we're looking at this one, we have half above, half below from the mean, because 1 minus 1/2 is going to be the negative point, or minus 1 1/2 is negative 0.5. So you're going to take the negative 0.5 squared plus the 0.5 squared, and we're going to divide that by the number in the sample minus 1, which is this. So what is 0.25 plus 0.25? 1/8. Is everybody okay with what I just did? If I look at this one's 1 above the mean and 1 below the mean, so 1 squared plus 1 squared divided by 1 gives me 2. What's the variance on this one? How far away from the mean are these values? They are there. There is no variance. This one stayed the same. So this one had a variance of 0. If we did this one, it's 1 above the mean, or sorry, half above the mean and half below the mean. So you're taking the 1/2 squared plus the 1/2 squared and dividing that by 1, so 1/4 plus 1/4 or 1/8 again. Here, this one has a variance of, and this one has a variance of. Okay. Now, actually, before we even figure out what the mean of the sample variances are, what is the variance of the population? So we have 1 below the mean. We have the mean, so 0 squared here, and then 1 above the mean, so the 1 squared. And we're going to divide that by the n minus 1. Actually, it's a population, so it's just divided by n. So I'm going to divide this by the 3. So we get a variance of 2/3. Because remember, the formula for variance for a population was different. And I'm not even seeing that we show that on here, which surprises me. I guess because we don't use the population as often. Now, I want you guys to find the mean of the sample variances. So what is 1/8 plus 2 plus 1/8 divided by 6? What is it? I'm hoping it's 2/3. Getting 3/8. Which part did I mess up on? Because it's half below the mean, going half below the mean and half above the mean, because that's what you're comparing it to. This one, I guess, should have been a negative 0.5 also. But once you squared it, it becomes a positive. And 1/2 times 1/2 is 1/4. Oh, how about I add right? What's 1/4 plus 1/4? Half. Those should be 1/2. 3 divided by 6. So the mean of the sample variances is going to be 1/2. Why is my answer not working right? It's still bugging me. We should be getting the population variance. Should be getting the population variance to be 0.816, which is still not the same population variance I'm getting here. Oh, shoot. No, I did do that. I squared those. X minus the means squared. Adding all those up and dividing by the n minus 1. I'm going to have to come back on this one because I've messed up somewhere and I'm not finding it. It's really starting to upset me and I don't want to waste a lot of time trying to figure it out. Because somewhere I'm just really wrong on calculating out my variances and I'm trying to figure out why. Because I should be getting a standard, I should be getting my sample, my variance of my entire population should be 0.816, not my 2/3. And these should be coming out to being an average of 0.816, not my 1/2. So both of my variances are wrong. So I'll show you guys next time. I'll fix it. I'll be back with it. So no. Yeah, well, it's going to have to last till Monday. So the sampling distribution of the variances is the distribution of sample variances with all samples having the same size n taken from the same population. The sample variances should and will, on Monday, target the value of the population variance. That is, the mean of the sample variances is the population variance. The distribution of the sample variances tends to be a distribution, though, that is skewed to the right. So if, and I'm going to wait until Monday to look at that one, once we get things figured out, but we'll look at that distribution of what our sample variances looks like because it should be skewed to the right, which means our tail should be heading towards the right, which is also backwards to what we've got going. The sampling distribution of the proportion is the distribution of sample proportions with all samples having the same size n taken from the same population. So if we go with the proportions, this one should work better. If I went with the proportion of ones that was in my sample, first of all, if we're doing it from the population that's 1, 2, and 3, what is the proportion of ones out of the entire population? Huh? 1/3. We've got 1, 1 out of the 3 numbers, so the proportion is 1/3 of the numbers are 1. Out of this one, what's the proportion of ones? 2 out of 2 of them are ones, so 1. Proportion of ones, 1 out of 2, so a half. Proportion of ones, find the mean of my sample proportions. So if I add the 1 plus the 1/2 plus the 1/2, we're going to end up with 2 out of the 6. 2 out of the 6 comes out to be 1/3. The mean of the sample proportions is the population mean. I'm sorry, is the population proportion. Does that make sense? So this time I was looking at the proportions, not the mean or the variance, but looking at the sampling distribution of the proportions. And so we're looking at having these. Now if we were to graph this one, we have 3 of them are at 0. We have the 1/2 has 2 of them, and the 1 has 1. I'm wondering if my problem is that I need to have the order matter. I guess I didn't label this. This was my population proportion was the 1/3. These were my sample proportions was the each of these. I'm still stick with trying to figure out. I think that might be my problem. I think my order might matter. And would that make a difference? I think my order must matter. Because if that's the case, then I would have, I've already got the 3, 3, I would have the 3, 2. I don't know. I'll come back to this one. It's really bugging me. Because that's not working out the way the things are at least working somewhat. I guess I kind of flipped through this one. We do need to distinguish between the population proportion P and some sample proportion, which was your P hat, represents your sample proportion versus P is your population proportion. So paying attention to our notation. Sample proportions target the value of the population proportion. That is, the mean of the sample proportions is the population proportion, which is what we saw. This is the one that's messing with me. The distribution of my sample proportion tends to be a normal distribution. And mine was not a normal distribution, which is why I think I needed to have both directions. I think the order must make a difference on those. So if we look at the unbiased estimators, sample means, variances, and proportions are unbiased estimators. That is, they target the population parameter. So if I am taking all my samples of the same size, and I take every one of those possibilities, and I find the mean of my sample means, or I find the mean of my sample variances, or I find the mean of my sample proportions, then that will be my population value. These statistics are better in estimating the population parameter then. These are unbiased estimators that they will get you, they're not going to try to skew that data from what it originally should have been. Does that make sense? So the mean of all my sample means will be my population mean. Now, so if I was taking, like I said, if we went with 100 NCMC students and we were trying, and that was, let's go statistics class. So if I take everybody in the statistics class and I found their ages, and I took every different combination of 5 students out of the statistics class, and I found the mean of that set of 5 students. So I'm taking the mean of this 5, finding another set of all 5, and every different combination of 5 stats students, and taking the mean of all those different sample means, it will be the same answer as the population mean was. If I actually just took everybody's age and added them up and divided by how many there are, I would find the population mean. Now, when it comes to reality, people aren't going to take the entire population and break the entire population into sets of 5 and look at all those combinations. But what we're aiming for next time is there's a lot of times that instead of taking the entire population, we just take a sample of the population. And I want to see if my sample is going to be good enough to estimate the entire population's value. So instead of taking every single NCMC student, if I can take a few samples of 30 students and find their ages, will it be good enough to estimate the population mean, the population's mean age, all NCMC students, without having to go through every single one? So that's where we're looking towards, is we're wanting these unbiased estimators. We want those samples to estimate what the population mean is. Now, notice the ones that were left out. Sample medians, ranges, and standard deviations were not part of that. They are biased estimators. That is, they do not target the population parameter. So the mean of the sample medians, where the median, remember, is that middle value, that's not going to target the population mean, the population median. If we looked at the range of all the different values, so if we looked at all the different possibilities with the range, where you had the 1 and the 1, the 1 and the 2, I'm going to just go with all combinations this time, 2 and the 1, the 1 and the 3 and the 1, 2 and the 3 and the 2, the 3 and the 3. Is that all my possibilities? I don't have 2 and 2 in there. I'm missing something, but I don't see it. So if I looked at all those, well, what's the range on this? 0. So if I'm doing the range, so this is the sample ranges. The range on this one is 1. The range on this one, range on this one, range on this one. Now, if I found the mean of those, actually I should ask this question. What's the range of 1, 2, and 3? We know the population range is going to be 2. If I found the mean of the sample ranges, am I going to approximate 2? If I added all these up and divided by how many there are, is it going to be close to 2? Hopefully you're just like a fast no, that's not going to be close to it, because we got a lot of zeros. We got some 1s. We only have 2 2s in this whole entire mess. And so everything, all those other numbers are going to drag it down below 2. It's definitely not going to say, hey, my range is 2. When you're looking for that range, you're looking for just those 2 most extreme. If I don't have both of the extremes in my sample, then my sample range is going to be smaller than the population range. Because you have to have both of the 2 extremes, not just the smallest and not just the biggest. I needed both the smallest and the biggest in my sample to find that sample range. And so the mean of my sample ranges is not going to be anywhere near the population range. And so trying to estimate from a sample what the range is going to be, not going to be very useful. Because trying to figure out, if I took NCMC students and I try to figure out the age, the range in ages that we have here, to figure out the range in ages, I need the youngest person and I need the oldest person. Same kind of thing goes with the median, finding that middle value. It's not going to, having that middle value is going to get changed a lot, and it's very dependent upon all those different values. And so it's not going to target the population parameter. Now, standard deviation's a little, we kind of use it anyhow type of thing. The bias with the standard deviation is relatively small in large samples. So S is often used to estimate. We already know that S squared, the variance, is used to estimate the population variance. There's going to be some bias, but the bias is not extreme enough for us to try to find a better way to do it. We will use the sample standard deviation to estimate the population variance, knowing that it's not going to be perfect, and knowing that my samples have to be big enough. And we'll talk about how big is big enough. And that's why in chapter 8, it's either 7 or 8, that we keep talking about having to have samples of size 30 or more. And this is the reason, because it has to be a sample that's large enough that the bias is not going to be very big. Oh, I've got those right there. I forgot I had it on the next thing. So to see that the range is a biased estimator, select two of the values, 1, 2, and 3 with replacement. Note the range should have been 2, and our range is definitely not 2. When I did this last time, I didn't let the order matter. I need to come back and I'll spend a lot of time on this one. Consider repeating this process. We roll a dice 5 times. You find the mean, and you find the variance, and the proportion of odd numbers of those results. What do we know about the behavior of all the sample means that are generated as this process continues indefinitely? So, I'm going to roll a dice 5 times. So each time I roll a dice, I'm just going to write down the numbers. I'm going to write it down 5 times, find the mean of those, and that's what I keep a hold of. I don't pay attention to what those 5 numbers were separately. I just find the mean of those 5 numbers, and that's what I'm keeping track of. Well, if I'm keeping track of the mean of my roll of 5 times, then I'm talking each of these are keeping the same sample size. They're all 5 in my sample. So the sample size is staying consistent. If we do this indefinitely, we do it a lot of times, then we know from what we just said, the mean of the sample means should target the population mean. So this is what we had. The first time I rolled it 5 times, my mean of those 5 rolls was 3.4. Next time I rolled it, I got a mean of 4.4, and then a mean of 2.8. And I continued doing this. I'm trying to find where it tells me how many times I did this. The mean of these 10,000 trials. So I'm going to do this 10,000 times. First of all, what do we know the mean should be if we are adding 1, 2, 3, 4, 5, 6 and dividing by 2? Population mean is 3.5. If you added up the numbers 1 through 6 divided by 6, we're going to get the mean to be 3.5. If we continue this process 10,000 times, and that's what this is showing. This is telling me the amount of times that I got 2.2 is my mean, and the 2.5, and all these different values, showing how many times we got this. Notice my graph is approximately normal. This is out of 10,000 trials, so it's getting to be a big enough amount of taking those samples. All outcomes are equally likely, so the population mean is 3.5. The mean of my 10,000 trials is 3.49. Very close to 3.5. If I continued this long enough, my sample mean would be 3.5. And also noticing that this distribution is a nice normal distribution. Questions there? So the mean of the sample means is the population mean. Doing the same thing, and every time I rolled that dice 5 times, now instead of just writing down the mean, I also found the variance. So I was putting those into maybe my list on my calculator, and I was letting it calculate out the sample variance every time. And notice it is the sample variance, which is your S squared. So these are each of the different sample variances compared to the population variance, which is the sigma squared, keeping track of that difference between whether we're talking about the notation for samples or populations. The population variance was 2.9. When they did this 10,000 times, the mean of the sample variances was 2.88. Again, it's targeting that 2.9. Is it exact? No, it's coming from samples. It's not the actual population. You're not including everything just the one time that it's included. But we're getting really close. And again, notice this time it's skewed to the right. Skewed to the right, saying that most of my values are the heavier, the larger amounts are moved to the left, and my tail goes out to the right a lot farther, where it's looking more like this kind of a distribution. So this one's skewed to the right. It's not a nice normal distribution. This one's skewed. My tail is going further out to the right. If we did the same thing, this time we were looking at the proportion of odd numbers in there. And so when you're doing the proportion of odd numbers and you're only rolling the dice 5 times, you might have 0 out of the 5, 1 out of the 5, 2 out of the 5, 3 out of the 5, 4 out of the 5, or 5 out of the 5. So that's the reason why this one's much more chunky. There's not very many other options. You can't get the decimals and fractions in between on this one at all. But we know if we took the proportion of odd numbers in the numbers 1 through 6, there's 3 odds out of the 6 numbers. So my population proportion would be 1/2. If we took the mean of all the sample proportions, it ended up being 1/2. Notice this is a pretty normal distribution. Again, this one's harder to see it being perfectly normal because it was only having 6 different chunks that it could fall into. But all outcomes are equally likely, so the population proportion of odd numbers is the 1/2. The proportion of the 10,000 trials was also 1/2. If I continued this indefinitely, the mean of sample proportions will be 0.5. Also notice that this is approximately normal. Questions, other than the fact that I can't get my numbers to work? Okay, those are your 3 problems to do. Don't forget to change your clocks this weekend. Our test is March 11th, so it's coming up next week also. But we'll use these pieces of information that we're doing today, we'll use those next time.